record. Okay, everyone. Now let's use this slides to go through the Gauss law again. We will spend 2 lectures to go through Gauss law and its applications. So what is Gauss law? So Gauss law is a more general statement about the nature of the electric field. Usually when we learn electrostatic or electrodynamics, we first learn Coulomb's law or Coulombic equation. Actually, Coulombic equation, you can consider it is a special or specific application of Gauss law when the charge is a sphere or it's a very small sphere or a point charge. Then Gauss law brings you the Coulombic equation or Coulomb's law. But Gauss law is more general. And Gauss law is very general. It's true for any cases, but there's some certain cases that we can use Gauss law to simplify the calculations to easily get quantitatively calculate the electric field. For those cases, we need symmetry. When symmetry is there, the complicated integral becomes simple calculations. So what is good symmetry? So here it shows one cylindrical symmetry. There are other 2 good symmetries. Can you think about if you remind yourself, you have learned Gauss law before, you have done some calculations in Gauss law before. What are the other symmetries that you used to apply Gauss law to them? Besides cylindrical symmetry, what are other good symmetries? The ring. The ring is a good symmetry, but it's not symmetry enough. It's not good enough for Gauss law. So in last class, we have calculated another example here. What's that symmetry? Do you remember? Yeah, spherical symmetry. So when you have a sphere, you can easily use Gauss law to convert it into a very simple calculation. What else? Can you imagine? So I suppose everyone have learned the Gauss law in your bachelor degree, right? So another common calculation using Gauss law is a symmetry of a plane, right? If you have a plane which is charged, then you can use a symmetry of a plane symmetry to calculate the electric field above and below this plane. So that's the 3 good symmetries. And the key for Gauss law, the most important thing for Gauss law is a connection. Gauss law is a connection between electric flux and charge. On the 2 sides of equation, if you think about the equation, one side is flux, electric flux. The other side is the charge, net charge in the surface, of course. Okay. Now, some basic ideas. The amount of electric field lines passing through a surface is called what's that? A, the flux. So when you use the electric field times the surface, or you can take it as how many field lines passing through a certain surface. and that's the flux, electric flux. So Gauss law is useful for calculating electric field that is what is your choice? A, symmetric. When there's a certain symmetry, then Gauss law might be very useful. So Gauss law applies to what? A line or a surface, flat surface, or a sphere, or an enclosed surface. An enclosed surface. So the two sides on the in the equation, it describes the flux and the net charge inside a closed surface. The surface could be artificial shape. Okay. Now, let's start from the symmetry. So suppose we know two things about electric field. The field points away from positive charge and towards negative charge, and then electric field exerts a force on the charged particle. So from those information, what can we deduce about the electric field of this charge distribution? A uniformly charged wire or a cylinder. This is a typical cylindrical symmetry. So first of all, let's ask a question. If the charge is distributed uniformly in a cylinder or a wire, then can the electric field distributed in this way? Is it possible? No, because let's say if this is infinitely long or very long, when it's very long, we can consider it in an ideal case. Let's say it's an infinitely long cylinder, and then it must have symmetry. So let's take a plane here. Let's say this is a reflection plane here. And on the left, it's infinity long. On the right, it's infinity long. So the left side and the right side of this plane should be symmetry, right? Then if this is symmetry, then if you do, let's say, if you reflect those field lines based on this plane, what will you get? You will get this field lines switch the direction. So that's impossible. So that means your field lines has to be perpendicular to the sides of the cylinders. Only in this way, if you make a cut or a reflection plane, then when you do a symmetry, then you have those field lines exactly the same before and after the reflection. So this is good symmetry. So if we look at the, let's say the cross view of the cylinder, then you will see a circle, of course. So another question is it possible that the field lines distributed in this way? Is that in a good symmetry? This is also impossible because if we have a reflection plane here, if you do the reflection, based on this plane. Will the field line be the same after the reflection? No, see, the direction will be changed. So this is also not a good symmetry. So a good symmetry of a circle surrounding the circle should be some field lines that cannot have a component tangent circular cross section, which should be something in the radial direction, like that. That's a good symmetry. Therefore, for a symmetry of a cylinder case or an infinitely long cylinder, then the electric field should go in this direction. If we look at in the side view, it is perpendicular to this cylinder surface. And if we look at in the cross view, it's perpendicular to the surface of the circle. In this case, if you, let's say, make a cut at anywhere, let's say this is a cut or reflection plane, if you do a reflection, your electric field doesn't change at all, right? And also, if you make a cut in this from the center of the circle and then do the reflection, then the electric field doesn't change. This is a very good symmetry. So this is a very good symmetry. Now let's see, for using Gauss law, there are three fundamental symmetries that can easily convert the integral into a simple calculation in Gauss law. The first is planar symmetry. Now suppose you have a plane which is uniformly charged, the charge density is uniform, and then you can imagine this planar symmetry involves symmetry with respect to first, translation parallel to the plane. Second, rotation above any lines perpendicular to the plane, and then rotation in the plane. So this is the base. This is the symmetry of planar system. So the thing above the surface and below surface should be exactly the symmetry when you let's say try to reflect everything above into below, you will have the same thing. And also, if you make a cut at any let's say any line or any surface which is perpendicular to your plane, and then do a reflection, you should get exactly the same thing before and after the reflection. And also when you do a rotation, this is your plane. If you choose one X, and then if you rotate the plane with the X, you should have exactly the same electric field. Second symmetry is cylindrical symmetry. In cylindrical symmetry, it involves symmetry with respect to translation parallel to axis, rotation about axis, reflection in any plane or perpendicular to the axis. For example, if you have this cylindrical distribution, if you make a cut at any cross section which is perpendicular to the direction of this cylinder, and then you do the reflection, the electric field should be the same after or before the reflection. And the third symmetry is, of course, a spherical symmetry. The spherical symmetry involves symmetry with respect to rotation and also reflection to any plane containing the center point. If you make a cut which is crossing the center of the sphere, using the cut plane as a reflection plane, then you do the reflection, the electric field should be exactly the same. Okay. Let me move this bar away. Okay, let's hide it. Okay, that's better. Okay, now the concept of flux. So we have learned flux is the definition of using electric field times your surface area. For example, if you have a box here, there might be some charges in the box. There will be some field lines going out. Then for each surface, you have some field lines. If you do a sum of all of those field lines coming out from the box, then you can calculate the flux. And from this electric field line distribution, you can recognize that the net charge inside the box is positive. And here, if you see the field lines are going inside, or you get more field lines going inside than the field lines going outside, that means net charge inside the box is negative, right? And if a box is surrounding the region of space and the charge is, the net charge in the box is 0, but there are some net charges outside the box, then the flux should be 0 for the surface of the box because there's no net charge inside the box. Okay, so what is Gaussian surface? So Gaussian surface is a closed surface. It's not necessarily to be a symmetry surface. It's not necessarily to be a sphere or a box or a cylindrical surface. It's not necessary. Any closed surface could be considered as a Gaussian surface. And it cannot even be a real surface. It could be an imaginary surface, for example, here, or in our previous calculation here in last class, when there is a sphere, we imagine there is a Gaussian surface at some position, and then we can do some calculations. It could be an imaginary surface rather than a physical surface. And the Gaussian surface is mostly useful when it matches the shape and symmetry of the field. For example, in figure A, it shows one Gaussian surface, which is cylindrical Gaussian surface. You can imagine there is a cylindrical wire or cylindrical distribution of charges in the center. And then you can draw a Gaussian surface, which is a cylindrical Gaussian surface surrounding the charge distribution or the wire charge distribution. If this is a three-dimensional view. If we look at the two-dimensional view first, the side view. For the side view, you can see the field lines are going left and right. And if you look at this in the top view, you will see the distribution of the field lines are in this way. Not every surface is useful for learning about charge. And consider the spherical surface in this figure here. This is the Gaussian surface, and the electric field tells us there is no charge, and it may be a point charge inside, but it's difficult to say. A Gaussian surface doesn't match symmetry of charge, isn't useful. As we show one example there, if you have a, if you remember that example, it's a half sphere. When there is a half sphere, it's impossible to make a Gaussian surface which has a good symmetry for the calculation. So the same thing here. We don't know what's inside here. It might be a charge on the left side of the sphere, But if in the Gaussian, in the application of Gauss law, if we put a surface in this way, so there's no symmetry on the left and the right side of the Gaussian surface, then it's difficult to, or it's impossible to use Gauss law to simplify the calculations. In this case, it's not very useful. So we can probably the charge is something here. So in this way, in this case, we'd better to make a Gauss surface, which is in the same center at the center of the charge, so that you can have a perfect, let's say, symmetry for your Gaussian surface. Okay, basic definition of flux. I think this is too details for you. The only thing we want to remind you is the electric flux measures amount of electric field lines passing through a surface area A whose normal to the surface is tilted in the angle theta from the field. Let's say if your electric field is going to the right side, however, your surface, the normal direction of your surface is not going to the right side, but it has an angle, which is theta, between your normal direction of the surface and the electric field direction. Then when you do the calculation of the electric flux, it can be easily calculated as the, let's say, EA cosine theta. This is a dot product between your surface area and your electric field. So there are some simple calculations. So let's say if you have electric field going in this direction, going to the right, and you have a plane which is parallel to your electric field, then what's the flux? Zero, because there's no perpendicular component for the surface to hold any of the electric field lines, or no electric field lines go through this surface. And in this case, you have a big surface, but the component which is perpendicular to the electric field line is not big. It's the surface times sine theta, which is a small area shown in the dashed line. So when you do the calculation, you can use a sine 20 degrees or cosine 70 degrees to do the flux. And in order to do the calculation or make the equations easier, usually we define a small surface or a flat surface to be a vector. Do you remember the direction of a surface? So a direction of a surface is the perpendicular direction to this surface, or the normal direction of the surface. So when you do a calculation of calculating the flux, you can simply use a vector product, a dot product between two vectors. First vector is the electric field, of course. The second one is the surface. And of course, the surface is now a vector. And then the flux can be easily written in this format, E dot product A. When you do a dot product, you have E times A cosine theta. By the way, the dot product of two vectors result in a scalar or vector? Scalar. That's the difference between a dot product and a cross product. Do you remember what is cross product? We'll use it a lot in this course. For example, now you have one vector going, let's say, to your left, the other vector going to the behind you. Then what's the cross product for vector 1 and vector 2? Right, it's going up, and it's vector 1 times vector 2 sine theta. That's the magnitude, and the cross product for two vectors, it's a vector again, but it's perpendicular to the two vectors. It's going up using your right hand rule. But for dot product for two vectors, it's a scalar, just EA cosine theta. Okay, so calculating flux, I think it's not a problem at all for you, just using the dot product. Okay, so integral, surface integral, using surface integral to calculate a flux. For example, now if you have a electric field distribution of E, it's not a uniform E. It's not a uniform electric field. It could be different in different angles, different directions and strengths at different positions. And you have a surface. If you want to do if you want to calculate the flux, then of course you can calculate little by little. First, cut the surface into small pieces. For this piece, it's EI times delta AI. For here, it's EJ times delta AJ. If you sum them up, you get the total or net flux for this area. If you cut them into infinite small pieces, then that's not a sum, that's integral. Then if you want to calculate the flux, the electric flux on this surface, what you can do is do an integral of E dot dA. And this integral, of course, is a surface integral. This is just a piece of surface. What about if the surface is a closed surface? When it's closed surface, when you do the integral of the E dot dA for surface, then that's the one side of your Gauss law equation. Okay, let's define electric flux through a closed surface to be an integral of a closed surface. That means a closed surface. A closed surface integral of E dot dA. Okay, so these are cross sections of 3D closed surfaces. The top and bottom surfaces, which are flat, are in front and behind the screen. The electric field is everywhere parallel to the screen. So which closed surface have zero flux? Which one? So who's going to choose A? Okay, so who is going to select the B or C or D or E? Actually, it's A. Let's see. B and C. So for B, if you still remember what you have learned for the definition of direction of the surface. Now, for B, let's talk about the surface at the right side. What's the direction of this surface? Do you still remember that? Let's say if you have a surface, it could be a closed surface, it could be a not closed surface, but now let's talk about closed surface. If you have a closed surface and you try to define the direction at a certain location, what's the direction of this small surface at this location? Normal. And going out, we define the normal direction as the direction of the surface, and it's going out rather than going in. So in this case, at this surface, the direction is in this direction. It's the same direction as the electric field line. Then if you calculate the flux on this surface, is it positive or negative? It's positive because the E and the A, they're in the same direction. So cosine theta equals to 1. Cosine theta is cosine 0 now because they're in the same direction. So you get a positive flux on this surface. The same thing for this surface and that surface. So for each surface, you get a positive flux. So totally, you have positive flux for the whole system. So for this one, do you get positive or negative flux for C? Negative, because let's take this as the example. This is your dA. This is your dA's direction. It's going out, but your electric field is in. Then the angle theta between your E and your dA is greater than 90 degrees. Then cosine theta is a negative number, right? So you have a negative flux. The same thing here and here. So you always have negative numbers on each surface. Then the total electric flux will be negative. So in this case, the direction of the surface is here, is in that direction and that direction. So on the right side, you get positive. On the left side, you get negative flux. And those two flux should cancel each other on the two sides because they're in a symmetry. If you do the calculation, they cancel each other, so it's 0. So now let's calculate the electric flux of a point charge. If you have a point charge in this way, and we draw a closed surface surrounding the charge, in order to make our calculations very easy, we try to make this surface, this closed surface, to be in the same symmetry as your point charge, which is spherical symmetry. And the center of this spherical surface is just at the center of the charge. So that in this way, your E on the surface is always perpendicular to the surface, and also the magnitude the magnitude of the E at any point on the surface should be the same. Then the flux is still a surface integral of E dot dA, and then E dot dA, it's a vector dot product. So it equals to E A cosine theta. Let's say cosine theta. So this times cosine theta. However, what is theta in this case? It's always 0 because, for example, at this point, your E is going to the right. And at this point, what's the direction of your surface? It's the normal direction. It's also going to the right. So because we have used this symmetry, so the direction of your dA on this surface is always in the same direction of the electric field. Then cosine theta is always cosine 0, which is 1. Then this is 1. So EA times 1 equals to EA, so it's EA. And A is very easy to calculate. E is constant, A is 4 pi r squared. Then A equals to 4 pi r squared, then you can easily calculate this flux to be E times 4 pi r squared. And then let's say and then what is E? E can be calculated by using Coulomb's law, which is Q over 4 pi epsilon r squared. And then finally you get this flux equals to Q over epsilon. So here we actually use the Gauss law, we use the Coulomb's law or Coulomb's equation to set up this equation, phi E or flux equals to Q over epsilon 0. But actually this equation could be extended to any cases, not only for a point charge. If you have multiple point charges, then in a sphere, this equation is still true. Or even if it's not a surface or spherical surface, it could be any surface which is enclosed, and it has even point charges or continuous charges inside the surface. No matter what, this equation is always true. It can be extended to more general cases. And this equation is so-called the Gauss law. So Gauss law just tells us the flux equals to Q over epsilon, over a constant in a closed surface. And this surface could be a spherical surface, which is used in our slides to derive the Gauss law. And this surface could be artificial surface. It could be in any shape. For example, even in a very complicated shape, still this equation is true. Let's say if you have point charge here, no matter what kind of surface you draw, for example, you can draw a surface which is in a spherical symmetry with your point charge, the flux should be exactly the same than any other closed surface which contains this charge. For example, you have a surface in the black line, which is in a complicated surface. If you do an integral, if you calculate the flux on that surface, it should be exactly the same as the flux on this red surface. Because you can imagine the flux is just the number of field lines. So the number of field lines should be the same on the red surface compared to the black surface. So the field lines are going to the infinite far away spaces if you have a charge like this. So any field line go through the red surface should go through the black surface. So they should have the same flux. But if you have a charge which is outside any type of closed surface, then you will have zero flux for this closed surface. For example, if you have one field line goes into the surface, into the closed surface, this field line will sooner or later, it will pass through and go out of this closed surface. Any field line from a charge which is outside the surface, it will pass through the closed surface twice. First time goes in, second time goes out. So if the charge is outside a closed surface, then the flux generated by this charge for this closed surface should always be zero. And then if you have multiple charges inside and close the surface, then the flux on the closed surface is only it only depends on the net charge inside the closed surface. No matter how many charges or what signs of charges, what distributions of charges outside the surface, it doesn't matter. So the flux on this surface depends only on the charges inside. It depends only on the net charges inside. For example, if you have 4 positive charges and 4 negative charges inside, then the net charge, the net flux on the surface should still be 0 if the net charge is 0. This is all due to the Gauss law, because Gauss law tells you that the flux equals to Q in over epsilon. Q in means the net charge inside the closed surface. Okay, now let's take this as a very quick example. So which option is right? Right. Okay, so let's do it by ourselves. Don't look at, let's do not trust the answer. So first, you have 15 out and you have 15 in. These two cancel. You have 20 out, 20 in. Those are canceled. Now you have 15 in, 10 out. So the net flux should be in or out? It's in. Then it should be negative. So the answer is wrong.
So I think there's another way to on go towards the direction.
Yeah, so for the flux, we only, now let's simplify it only to be 2 directions, out or in. So if the out is greater than in, then it's positive charge inside. Net charge is positive. If the net flux is in, that means net charge is negative. Okay, so which one do you think is right? So which one? Which one has larger electric flux? Okay, who's going to choose A? And who chooses B? Or C? Or D? Okay, so the answer is B. This time he's right. Because the flux depends only on the net charge inside the closed surface. If you draw a smaller surface here, which is as small as this A surface, it still has the same flux as the bigger surface have, because any field line goes through the bigger surface, it must go through the small surface. So the number of field lines should be the same, the flux is the same. Okay, last question. Which one do you think is right? Okay, let's see. So who chooses A or B or C or D? Okay, great, great. So net charge is the same, and then when you use Gauss law, everything is the same. So it doesn't care. It doesn't care what's the distribution inside. As long as the symmetry, then no matter it's a small sphere or bigger sphere, so you will have the same result. Okay, so that's the, let me see. Do we still have some time? Oh, we still have some time. We can take a break, or let's do not take a break, but continue our class so that we can finish it earlier. Do you need a break? Okay, I don't need it too. Of something, it's not very hard. Okay. Before we finish the class, let's see how to use Gauss law to solve problems like we did on the blackboard last time. So Gauss law applies only to a closed surface called a Gaussian surface. A Gaussian surface is not necessarily to be a physical surface. It could be an imaginary surface. And when you use Gauss law, if you find the perfect symmetry, it will be very useful to simplify the calculation. Otherwise, the Gauss law doesn't help you much, because once you need to do a complicated integral on the let's say irregular surface, then the problem could become very difficult. And the Gauss law is simply written here. Your flux equals to the net charge over a constant, which is epsilon. And the flux is easily calculating by an integral on the closed surface of the flux, which is E dot product dA. Okay. This is a quick question. A spherical Gaussian surface around a dipole. Net charge is 0. So what is true? Okay, so Who's going to choose A or B or C? Okay. So first of all, this is a Gaussian surface. Gaussian surface could be a physical surface, but most of the time it's an imaginary surface, like in this one. You can think this, it doesn't exist. So let's ignore the Gaussian surface. If we ignore the Gaussian surface, what does the field line look like? Right? Is that right? Sorry, it's wrong. The curvature is wrong. Let me see. Let me erase it. Is it right or wrong? This line is wrong. This line is wrong. This line is wrong. This is also wrong. Why? Because the curvature. What happened? I can't erase it. Because the curvature should be in this way, right? Rather than in that way. So ignore the wrong field line. It should be something like that. So is the electric field zero at the surface here? It's not zero, it's going in this direction, and also they're not zero. So what is zero in this case? Flux. Because first the net charge is zero, then this surface hold a zero net charge system, then on this surface, the flux should be zero. So the answer is B. So that's the field line. That's a little bit complicated. Okay, outside the surface of charge, if you have a charge inside, how to calculate the electric field? We have done that here in last lecture. So we are not going to go through this example again. So infinite plane of charge, how to calculate? So in previous example, we show how to calculate the electric field for a spherical charge. Now, if you have a charge distributed uniformly on the plane, how to calculate the charges? So first of all, if you have a plane which has uniformly distributed charges, then first of all, what's the direction of those field lines? Let's say it's positively charged plane. So what's the direction of your electric field? It should be perpendicular to the plane or normal direction of the plane. Let's say if this is your plane, it's a positively charged. So on the surface above, you have field lines go up, and at the surface below, you have the field lines going down. So, so that's the direction of E. So in this example, you have the E perpendicular to the plane going to the left and right. If we know the charge density, can we calculate the electric field for such a charged plane? The answer is yes. So let's calculate the electric field at this point, which is away from the plane, and the distance between this point and the plane is L. And the charge density, let's say it's eta or something. And then what we can do to calculate the electric field is I should leave it as a practice for you. Okay, let's do it first by yourself. Now you have a plan. You know the charge density is eta. It's in the unit of coulombs per meter squared. And the distance between your testing point and the plane is L. How to calculate the electric field at this point? So I'll leave it for you after the class. Let's stop here. So take 10 minutes or 15 minutes to solve the problem. And let's continue our lecture on Thursday. And first see if your calculation is right. And then let's continue to several other examples of applying Gauss law in different systems. Okay, so that's all for today. Let me stop sharing and let me